I'll explain to you how I was able to figure out what the possible samples are. Each time I wrote out a different sample of 3 people, I just left out one person from the population. So when I wrote out sample 1, I left out person 4. When I wrote out sample 2, I left out person 3. When I wrote out sample 3, I left out person 2. And when I wrote out sample 4, I left out person 1. So if you want to write out all possible samples of 3 people from a population of 4 people, all you have to do is just leave out one person each time. It's pretty straightforward. And if we calculate the mean of each possible sample of 3 people, and then we write out those 4 sample means over here, those 4 sample means will make up the sampling distribution for the sample size of 3. So let's do that. We can calculate each sample mean by just adding the 3 numbers in the sample and dividing the total by 3. So if you add these 3 numbers and divide the total by 3, you get 56. If you add these 3 numbers and divide the total by 3, you get 56.67. And these are the other 2 sample means. And now that we know what the 4 sample means are, we'll just list them out over here. And these 4 sample means make up the sampling distribution for the sample size of 3, because these are just the means of all possible samples of 3 people that could be selected from this population. And you might have already noticed that these 4 sample means are packed in closer to the population mean than the 6 sample means that we had in our last example. And if you notice that, you would be correct, because when you go up to a bigger sample size, the sampling distribution moves in closer toward the population mean, and it becomes less spread out. And that makes sense because larger samples are more accurate than smaller samples. At this point, I wanted to discuss the mean and standard deviation of a sampling distribution. A sampling distribution is really just a collection of numbers. So just like any collection of numbers, a sampling distribution has a mean and standard deviation of its own. It turns out that the mean of a sampling distribution is always equal to the mean of the population. And I'll actually demonstrate this point right now. Let's go back to this example where we were looking at the sampling distribution for the sample size of 2. If we add these 4 numbers over here in the population and divide the total by 4, we'll get the mean of the population. If we add the 6 sample means of the sampling distribution and divide the total by 6, we'll get the mean of the sampling distribution. And if we did that, we would see that the 2 means would come out to the same number. So the mean of the population equals the mean of the sampling distribution. These 2 means have to come out to the same number. And we can see here that they did come out to the same number. They both came out to 57. So the mean of the individual people in the population always equals the mean of the sample means in the sampling distribution. This symbol, which is the Greek letter mu, is a symbol for population mean. So that's why I use this symbol over here to refer to the mean of the population numbers. This symbol right here, which is mu x bar, is actually the symbol for the mean of a sampling distribution of sample means. The reason why the symbol is mu x bar is because it's the mean of the sample means. I would think about it that way. Let's now look at another example of how the mean of the population always equals the mean of the sampling distribution. Let's go to our, well,